Let's consider a symmetric positive defined matrix system. And the number of iterations is proportional to the square root of the condition number. So you can see that a number of iterations is in the order of n power 0.5. We discussed the concept of computational complexity earlier. In our case, a computational complexity of solving a simple Laplacian equation problem is n power 1.5. And the above simple result can also has a physical interpretation. There's a number of iterations need to solve Laplacian problem is roughly proportional to n power 0.5, and this follows from the fact that the differential equation operator gives rise to a sparse matrix system. It accounts for only near-neighbor interaction. So therefore, each matrix vector product will send the information on the order of 1 grid point away. And because of it, it takes on the order of n power 0.5 steps to send the information entirely through the simulation region. So we conducted these estimates for the one-dimensional problem. It's n power 0.5. And in the three-dimensional case, this translates to n power 0.33 steps, and it yields a computational complexity of 1.33. And I would like to mention one more aspect related to the case when we employ matrix preconditioning. So the above matrix system for 2 dimensions can be preconditioned to give a condition number proportional to n power 0.5, and it yields a final computational complexity of n power 125. In 3 dimensions, with preconditioning, this reduced to n power 1.17. So the consideration for the Laplace operator are straightforward because it's always negative defined. However, it is more difficult to establish the convergence of solving the Helmholtz equation. So in this case, we solve a matrix system that responds to this equation. And as you know here, k square is positive defined and Laplacian operator is negative defined. So because of this, the resultant operator is indefined. We can't say whether it is positive or negative. And again, I would like to remind you that this happened when we solve the above equation in a closed region with Neumann or Dirichlet boundary conditions. So this indefinitely become important in the case of the possible resonances in the closed surface. And to be specific, for the resonance case, the eigenvalue of the above system is 0. So if we attempt to solve the Helmholtz equation iteratively for closed cavity, we can find out that the solution might not converge at all at the resonant frequency. If we translate it to the fine difference method, this non-convergence implies that it takes infinitely many time steps to solve the wave equation in closed cavity. So here the key term is a closed cavity. We can mitigate this problem of the non-convergent solution in the resonance, and for that we need to let the energy radiate to infinity. And computationally, we realize that by adding absorbing boundary condition to absorb the energy at the edge of the simulation region. The result, the system will not have a zero eigenvalue, and we can avoid computational problem of ill-convergence. So let me repeat what I've just said, but slightly differently. So based on the above consideration, we conclude that it's important to estimate the asymptotic computation complexity of solving Helmholtz problem. It occurs due to inability to define whether the matrix is positive or negative defined. There is also a possibility of encountering a structure resonance. However, we can have some consideration for Laplace problem because Laplacian operator is always a negative defined operator in a closed region with Neumann and Dirichlet boundary conditions. So we can recount the asymptotic complexity derived from the Laplace problem to be the lower bound of the asymptotic complexity for the Helmholtz problem. And the above physical picture of the convergence rate lends insight into designing method to accelerate the convergence rate for the Laplace equation. We can design a coarse grid to propagate the information across the simulation region rapidly. Then we interpolate from coarse grid to fine grid and vice versa. This way, we can capture high spatial frequency information to obtain computational results with high accuracy. So these notable features are called the scale invariant nature of the Laplace equation. We can build an hierarchy of measures of different coarseness for this purpose, and this should already be familiar to you because earlier we discussed similar concepts for approximating solutions, provided we know the results of different grid sizes. So for the case of more complex problem, we have an use an advanced approach. This is known as the multi-grid method. So one can show that the number of iterations can be made independent of the size of the problem. And in this manner, we can then solve the Laplace problem in order of n operations. And unfortunately, there is a limitation on accelerating the solution time of the Helmholtz problem using this multi-grid method. Solution of the Helmholtz equation is oscillatory, and due to the Nyquist sampling theorem, the mesh cannot be made arbitrary coarse. So the theorem states that these 2 points per wavelength are needed to fully capture the information on the oscillatory function. And this barrier to coarsification is called the Nyquist barrier. And finally, I want to make a last point on this topic. The above discussion will for Laplace and Helmholtz equation, but we can regard the property of static electromagnetic fields as Laplacian in nature instead of dynamic electromagnetic field is Helmholtzian in nature. So the final difference methods in numerical time integration of equation can be done explicitly or implicitly. And the main advantage of the explicit scheme is the possibility of solving each time step without the need to solve the systematic system of equation where all the degrees of freedom are involved. So its disadvantage is stability of the solution, which in many cases leads to time steps that are too small to be efficient. And on the contrary, implicit method always allows stable time steps under certain condition, size of which must be regulated only by precision criteria and not stability criteria. And in return, there's a disadvantage of a system of equation involve all degrees of freedom must be solved, making the method costly and difficult to parallelize. So the implicit method is a Krohn-Nicholson method, and its order approximation is equal to t square plus delta x square. And this method has the advantage of being unconditionally stable. Right, this is the case here, number 2. So the instability phenomenon does not appear in the solution that was seen for explicit method. Implicit scheme been extensively used for improved stability condition. However, these schemes require important sub-iteration, and it is a method disadvantage. So the main advantage of the first Frankel scheme is this last one is that to be twice faster than Krohn-Nicholson, and to compute the solution explicitly at each time step to be unconditionally stable and easier to parallelize on high-performance computer system. However, the approach is unconditionally stable, and the choice of discretization in time or in coordinate remains an important issue in accuracy representing the modeled phenomena. So the standard for Neumann stability analysis shows that Dufers-Frankel scheme is unconditionally stable. And for such scheme, the choice of time discretization depends on the variation of the boundary condition and the equation coefficient for the diffusion time and the material to compute a solution accurately representing the physical phenomena. It's not correct to assume that the unconditionally stable property implies a physically realistic solution will always be provided. So we can't assume that the solution is accurate no matter how large time step is. And the stability of the numerical method only ensures that the solutions in the solution will eventually decay out, but it does not guarantee physically plausible solution.